Okay, here we go again with intermediate value theorem. This time we're going to apply this theorem to tables instead of graphs. So same logic as before, it's just a little harder to see what we're thinking because the graph is not given to us. Okay. So let's take a look at an example. I've given you the theorem again here. Let's remind ourselves what it's saying. It's basically saying that if f is continuous and the function passes a certain y value, it has to be equal to that y value at a certain point, right? So this would be, in this formulation, n would be this y value, this would be a, this would be b, and this would be c, right? Okay, so let's look at our first problem here. This is straight off of Delta Math. So selected values of the function f are shown in the table below to determine the validity. Validity is just a fancy way of saying truthfulness of the following statement. F of x equals 0 has at least two solutions in the interval 0, 9. You're like, what in the world could that mean? I don't know. Well, we might be thinking that yes, this is true because f of x equals 0. Notice f goes from negative to positive here, and then from positive to negative here. So it has to cross 0, right? But they didn't tell us that f is continuous, and we don't know what f is. We just have these selected values. So here we'd say, like, cannot be determined. I forget what it says on Delta Math. Let me check that. So this one, we'd say either true or false. We don't know, because they didn't say f was continuous. So this could be a situation where we have two different pieces, right? So we have 0 here, and then a gap, and then the function continues. Or it could be a situation where we have 0 and the function just continuously goes through it, but we don't know. Okay? So anytime it doesn't say that f is continuous, we have to say either true or false. We don't know. Let's look at one where the intermediate value theorem does apply. Okay, here we go. So as we read this one, that word continuous, okay? So that means that the intermediate value theorem does apply. Remember, that's called the hypothesis of the intermediate value theorem, that the function is continuous. That is true, so we're going to use it. And then we don't really need to know about the derivative. This says that the function is decreasing for everywhere in the interval. Doesn't really matter though. F of x equals 3 has exactly one solution on the interval from 0 to 4. Okay, so what we're looking for is whether this value of f of x is between two values of f of x in the table. And obviously, like, f of x equals 3 would be here, right? Because 3 is between 1 and 4, and if the function is continuous, that would mean, like, we'd have this point 1, 1, and this point 0, 4. 0, 4 should be up here, right? And then 3 would have to be somewhere in between, right? So that's all we're saying. So this would be, like, definitely true. And it's true because the intermediate value theorem applies. Easy as that. So no real math happening here, right? We're just checking to see that the function is continuous, and then checking to see that this y value has a place to live in the table between two y values that are given. Okay, here is another one. So first thing we're going to check, right, we're going to see if the function is continuous, and it is. Continuous function f. And then we want to know about this particular statement. And this one's a little different than the last one. So we have f of x equals -6. Notice -6 falls outside the bounds. So our function, as we see it, goes from -4 to 24. But -6 must be down here, right? So here, the intermediate value theorem applies, but -6 is outside the bound. So -6 would be, another way to think of it would be here in the table probably. So this one would be not necessarily true or false. Okay, so not false because the function could easily do something instead of how I drew it here. The function could easily start at the same spot, but then kind of dip down and go back up. Right? So here we'd say either true or false. Okay, we'll do one more example. Okay, here's where we have to think a little bit harder. So when you see that the statement that we're looking at is a two-solution statement, that's when you really have to dig in. Okay, so exactly two solutions in the interval of 3 to 8. So the first thing I'm going to look at is that this interval matches what we have here, and it does it. We have 3 to 8. And then I'm going to look to see if f of x equals 0 falls between my y values. So f of x equals 0 would be here, right? Falls between -1 and 1 and -5. But exactly two solutions, so it only shows up once. So here's where we go back to the text, and here's where the derivative matters. So this derivative, if you remember from our 1.3 lessons, means that f is strictly decreasing. So the derivative is everywhere negative. Again, this is hard. This is hard logic. F is strictly decreasing. Okay, that means from 6 to 8, my function goes only downhill. We know that this is -5. This is 1 up here in terms of my x and y values. 0 has to be somewhere in the middle. Okay. So notice if f never goes back up, it never crosses that 0 line again. So if the function is decreasing everywhere, you can't have exactly two solutions to f of x equals 0. F of x equals 0 can only be true once. So this one is definitely false. The two solutions ones are the harder ones. Even if you miss these sometimes, if you persist through them, these are straightforward enough that I have faith that you'll finish the assignment here.